You can't really talk about storage at Google without talking about how our production systems work. How are all the hard disks and flash drives on individual machines connected? Let's boil it down. Data is stored in hard disk drives or solid-state drives. SSDs and HDDs are deployed separately from the applications. For example, they can be stored in a dedicated storage tray like this one. In other words, we separate storage from compute. Data needed by a machine is typically not even in the same rack because machines can access data in a different physical location through our robust global fiber network. Splitting storage and compute lets us scale them independently as demand grows, and machines can process requests much more efficiently. We organize storage and compute racks into rows of physical enclosures, organizing groups of enclosures into clusters, and putting multiple clusters in a single data center. Each cluster depends on their own power, cooling, and network infrastructure, a deliberate part of how we design for data protection and reliability at scale. We've built our own warehouse-scale machine out of hundreds of thousands of relatively inexpensive machines. At Google, it's rare to dedicate an entire storage appliance in our data center for storing only one product or service's data. Instead, we spread a workload's data across multiple machines, and workloads share network access to that storage. Encryption is inherent in our storage systems, and all data is encrypted prior to being written to disk. But how does Google make storage accessible and scalable across a global fleet of machines? Remember, at planetary scale, it's not unusual for individual machines, racks, or even entire buildings to periodically fail. So we need to build software to make the data stored on them durable. That way, when they fail, no data is lost. Every layer of our storage stack, down to the file system and the layer that writes to storage devices, is a shared service. Services like search, photos, and Gmail workloads share machines at the data centers. Resources within each machine, like compute and memory, are allocated to each service. At a machine level, disk, or D for short, is the system that exposes the hard disk and SSD drives attached to individual machines to other services in the cluster. It manages access to each machine's disk capacity to maximize utilization. At the cluster level, most data we store has high durability and latency requirements, so we built a file system called Colossus on top of D, which is a foundation for many services like cloud storage and Bigtable. At the Colossus level, files are broken down into a set of chunks that can be stored on different machines in the cluster. This data replication across machines is the key to fast recovery and fault tolerance against things like network failures. For a given chunk, Colossus identifies a machine to write the chunk to, and the client sends the chunk to the D service that runs on the target machine to perform the write. Security is ensured through the encryption of each chunk, and each chunk has a unique encryption key. Because a single machine can be running multiple services, and conversely, a service can be running on many machines, services are constantly adapting to the amount of resources they use. Now you can see how distributed data better utilizes our machine capacity and gives Google Cloud Services higher reliability and performance. For Google Cloud users, you have the option to store data on local solid-state drives, zonal persistent disks that map to clusters across zones in the same region, or regional persistent disks across cloud regions or even storage buckets. You can store data in a single region for high performance, dual region for high performance and high availability, and multiple regions for the highest availability. Your data maps to different clusters and protects it from zonal and regional failures. D and Colossus manage access to the storage, store data safely and securely, and efficiently use our hardware so you get the best performance possible. All of this is possible because of the speed of our network fabric. More on that next time on Discovering Data Centers.